Hello friends, myself Nitin Patil. I am working as assistant professor in Department of Computer Science, Savitribai Phule Pune University. I will be taking complete walkthrough from the source code of assembly program. Generally, we do write assembly programs mainly either in Intel 32-bit architecture or 64-bit architecture. So, what are the process that is carried out by the assembler to translate your assembly code to object code? I am going to have a complete walkthrough in that particular process. So, how the instructions are getting translated to what we call as object code. So, for that purpose we will require one special document which can be downloaded from Intel website. So, I have downloaded that file for our reference. So, it is called as 64I32 architecture file which is available on Intel website. So, we are mainly concentrating upon this particular chapter number 2. So, if we see like this is what is the instruction format followed by Intel architecture. So, these are completely 6 components included over there. First component is called as instruction prefixes, second one is opcode, third one is ModRM byte, fourth one SIB which is called as scale index base, fifth one is displacement and sixth one is immediate. Now, few of these components would be optional, like almost compulsory would be what we call as opcode. So, rest of the components would be available depending upon what instruction you use. So, as in a sample case what I will do is I will write one sample program using IA32-bit instruction set and we will completely see how the translation is done. So, let me type test.asm. So, here we will start by typing, say I am adding some data elements over here. So, let me declare one variable called a of type db. This would be a string, this is a string, say for a while ended with /n and 0. Then I am declaring one variable b which would be of type double, defined double, and say I have given values to it as 10, 20. Now, let me type section dot text. Now, as I am using NASM as an assembler to translate this, and what are the object code that this NASM generates. So, I am going to make use of LD as an linker which internally is inbuilt in GCC component. So, GCC requires main as a function. So, I am using that. So, that is why we have to write global main where our source code will start, and let me type few instructions over here, like for example move EX comma ABX, move EBX comma ECX. Now, if you see the format is what first instruction when we talk about move EX comma ABX, I mean by it like contents of EBX should be transferred to EAX, and same way for ECX content should be transferred to EBX. Now, let me add one more instruction, like for example add EAX comma EBX, even let me add move EBX comma 10, then even move ECX comma 10. So, you will see that I have specifically picked 2-3 instructions over there which are so similar. So, let us save this code and let us translate it. So, as I am using GCC as an linker which internally makes use of LD as a linker, that is why. So, I am purposefully creating an ELF file which is of 32-bit, and if I translate this program using this assembler using this particular thing. So, it got created. Now, I really wish to see what is the object code generated from this file. So, let me write -l which generates a listing after the translation phase. So, let us say I have created one file p.lst. Let us see what are the contents. So, when we display contents of it, one can see over here that our code is shown over there towards right pane and on the terminal, and towards left pane we will see that some code, some object code or hex code is written there. So, even there are some line numbers added. These line numbers are added by your NASM while you really, or any assembler will do that, but for a while as we are using NASM as a case. So, if you see section dot data started with A and there is a string we have written, this is a string then 10 comma 0. Now, if we see this is a string which is taken as an input by us, which is ending with 0. So, here this 10 means /n and this 0 means /0. So, if we see over here, this is complete translation, like these numbers, this one, this set and this other set is the number which exactly translated that ASCII characters to hex. So, if we say T, capital T's ASCII value would be converted to 54, and same way, like if we go on, when it ends towards the end we have 10 and 0. So, one may see there like 10 is shown over there as 0A and 0 is shown as 00. Okay. Now, then second variable that we took is B. Now, if we see the values given to it, as we have taken as DD, DD means it should take 4 bytes. So, the values that we gave are 10 and 20. So, one may see here that it has written it using some Indian notation, which in brief we are going to talk about later. So, this 10 is converted to 0A and this 20 is converted to 14, which is hex equivalent for 10 and 20. Now, one may see here like section dot data, the addressing started at 0, fine. So, if we see this particular character, this character T would be represented as 54. So, if we compute these characters including this 10 and 0, 10 would be treated as single character, 0 would be treated as a single character because they are defined as a byte. So, if we compute this, what are the number of characters that are here, you will see that double the digits are. Say for example, T would be represented by 54, then H would be represented by 4 and so on. So, as we see that I is a repeated character here, 3 times it appeared. So, one may see that one digit with respect to I, like for example, here in this case it is THI 69. So, this is I, one may see again there is. So, this is I. Again one more time we have seen that it is appearing towards STRING. So, this is I. So, this is how the data part would be translated into hex. Then let us move to section dot text, where exactly your code is written, and your code translation will start from the first executable instruction. The instruction in this case is now move EX comma ABX, then move EBX comma ECX and so on. One may see here like for each instruction like it's say it started at 0, it had some code like 89D8 for a while. Then second instruction is there which started at 2. Now, how this is computed, like let us see this particular instruction. This instruction after translation took total 2 bytes. Now, those 2 bytes one may see over here like 89 and D8. Now, after this translation one may see that this would be stored at 0, this would be stored at 1. Now, second address started. So, address bit 2, then 2, 3, then one may see again 4, 5, then 6. Now, if you see this instruction, we have written move EBX comma 10. Now, here we exactly know that 10 is translated above even like as 0A 0000. So, you can see over here as well that 0A 000 like it comprises 4 bytes because the 10 is converted to 32 bit value as per the nomenclature. Now, move EBX, move ECX, one may see here that it is having some code over here. So, if you see in each of these instructions when it got one to one translation, for first instruction one may see 89 dB, for second translation we can see 89 CV. Now, how it got computed? So, for that purpose what I will do is I will take one text file for you to really show how exactly it is happening. So, say our instruction is move EX comma EBX. Now, let us try to see what the instruction format tells us. So, this is what our instruction format is. As one can see here, there is a opcode thing and there is something called as ModRM. This ModRM specifically tells you what are the types of operands. Now, if the operand contain register, some address, or maybe rather one may say like some memory reference that you have added, or even immediate data, its reflection can be seen over there. Now, this ModRM requires 1 byte to store. Okay. So, which is divided into different 3 components. So, starting from lower bit to higher bit, from 0 to 2 there would be R/M, okay, register or memory. Then from 3 to 5 there would be register number, and 6 and 7 relates to what we call as mod. So, when we see this will be a completely binary number. So, in this case there would be 4 possible mods 00, 01, 10, 11. In these few initial sessions, we are going to mainly concentrate upon two mods, one is 0 0 and one is other one is 1 1. So, as an a case, what I will do is I will take this first example which you have taken as move ex comma ebx. So, let us go into this Intel manual and try to find out where the move instruction can be seen. So, in fourth chapter rather, if you see, all instructions starting with M to U would be added. So, let us see move. So, we got move, fine. So, if you see here, there are this is a table displayed over there which talks about opcode for the instruction, how the instruction format would be, and few other information related to that instruction is added. Now, the instruction that we have taken is move ex comma ebx, and if we see the translation that is applied for it is 89 dB, fine. So, let us find out where this 89 is. So, in this file rather, if we see this 89 is available here at these two different places. So, move RM R16 and second case is move RM 32 R32. Now, what are the code that I have written? My code contains all 32 bit registers. So, we are mainly concentrating upon this 32 thing, fine. So, 89. So, if you see there is something called a slash r, this slash r tells us that in the instruction after 89 there would be mod RM byte available. Now, what this instruction does, its detail even can be seen over here. So, it says move register 32 contents to either a register or memory reference. Now, in this case we haven't used rather any memory reference over there, but we have used specifically a register because our instruction itself is telling us that the instruction is move ex comma ebx. Now, how exactly we are going to communicate to the system that I have used this specific register. So, what happens is like when we saw that mod RM byte above, this mod RM byte will have that particular instruction divided into three different components: mod, register opcode or register memory. In this case, we are having both of the operands as registers, correct. So, let us see how exactly this would be done. Now, if we should know now when which register is used. Now, what Intel did rather for helping the users to for helping the programmers to write these translators, each register is given some specific number. So, I am taking this particular table which says 32 bit addressing forms with mod RM byte, fine. Now, you may see that few registers are written here AL, AX, EAX, then CL, CX, ECX, then DL, DX, EDX and so on. Like if we move further, there are like DL, DX, EDX, then BL, BX, EBX, AH, SP, ESP, CH, BP, EVP, DH, SI, ESI and DH, DI, EDI. Now, these registers are like few of them are 8 bit registers, few of them are 16 bit register and few of them are 32 bit registers. Now, each 32 bit register started with E, okay. Rest of them like AX, CX, DX, BX, SP, BP, SI and DI are 16 bit registers. AL, CL, DL, BL, like when you take 16 bit registers as AX, so you divide it into 8 partitions. So, lower side things would be referred, lower side bits would be referred as AL and higher side bits of that 16 bit would be referred as AH. Now, the numbering is specifically done. How the registers are arranged are like EAX first, then ECX, EDX, then EBX. Now, generally whenever we talk about registers used by Intel, so we do say EAX, EBX, ECX, EDX, but order that is applied in translation is EAX first, then ECX, then EDX, then further EBX, ESP, EBP, ESI and EDI. Now, for each of these registers the numbers given are 000, 001, 010, 011, 100, 101, 110 and 111. So, this is this in the same order, the way that I pronounce these all things like EAX, EBX, EAX, ECX, EDX, EBX, ESP, EBP, ESI, EDI. So, this number would be like triplet would be formed using the binary representation. So, let us see like what we have is we have first instruction as move EX comma EBX. Now, for EX and EBX, what are the numbers? For EX we have number as 000 and for EBX we have number as for example here is 0 1 1. So, if let me write them like I have EAX as 0 0 0, for EBX I have 0 1 1, fine. Now, I have to write that mod as well. Now, one interesting thing that can be seen over here is like this would be written in a cross, like you may see here I have written EX here. So, towards the lower side I am adding this one, fine, like EX representation as 3 zeros would be written towards the lower part of bit, then EBX would be picked and written over here to the next, rather next 3 bits from the lower side, first 3 bits then next 3 bits. Then as we are having this instruction between register to register or a register to some memory. So, in that case always the mod, the type of instruction would be register to register. So, it makes use of representation as 1 1. So, what our instruction lead to, our instructions mod RM byte would be 1 1 0 1 1 0 0 0. So, if I divide these two into group of 4 bits. So, let me try to find out what is the representation used for this 1 1 0 1. If I convert this to hex, so it would be 8 plus 4 12 plus 1 13. So, A is 10, B, C, D. So, it would be D, and if we take this particular one, this is 8. So, now one may see here that when we wrote move EX comma EBX, we got this D8, fine. That means what? For this instruction whenever there is a move from one register to other register, the opcode would be written as 89 and in front of it the mod RM byte would be written as 1 1 0 1 1 and 0 0 0 when operands are EX and EBX. So, this binary would be translated to D8. So, towards the end my code would be 898. Let us try to see what would be the code further. So, as we already said that the numbers that we are going to use are EAX, ECX, EDX, EBX, ESP, EBP, ESI and EDI. So, numbers we have said as 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0 and 1 1 1, fine. So, if my instruction is say move EBX comma EX which we had earlier. So, move EBX comma EX. So, I will write that instruction over here move EBX comma ECX. With the earlier strategy we should write now the code. So, I will write EBX code here. So, it would be 0 1 1. What is ECX code? So, ECX code is 0 0 1, correct. So, I got this. Now, my mod is 1 1. So, now let me combine together these 4, let me take this one. Now, let us convert this to hex. So, 8 plus 4 12 A B C. So, I got C, fine. Now, I have 1 0 1 1 8 plus 2 plus 1. So, it is 11. So, 11 leads to B. Now, what it means like whenever I have EBX comma ECX as an operand for move instruction, then it should translate that to that mod RM byte should result to something called as CB. So, now before this my opcode would be what 89. So, translation of my code should be 89 CB. Let us see over here what we got. So, we got 89 CB, correct. So, that is how it is done. Now, let us see further, there is a instruction called add. Now, this also is an register to register instruction. So, if you see the first instruction that we took is containing the similar parameters as EX comma EBX. So, now I am using similar operands over there with add. So, that mod RM byte should not change. So, one may see over here in the code we got D8 for EX EBX, same case would be here as D8. Now, what is changing is the opcode. That opcode itself is telling us that okay which kind of instruction it is. Further, let us see what next instruction is. Next instruction we are having is say for example add EX comma EBX. As I said, let us see what goes there. So, we have to find out instructions starting with A. So, I will go to this chapter 3. So, this talks about all instructions from A to L. So, I will pick instruction add from it. So, I got it add, fine. So, let us move this. So, let us find out where is register to register, fine. So, add register 32 to register 32. Now, one interesting thing here is Like whenever we do talk about this add ex comma abx, we know that it is register to register, but how the opcode should be. Now we haven't seen where this 89 is. I will show after a while. Let us first see this particular one, add ex comma abx. Now if you see add ex comma abx, we already know now how to compute this d8. Let us say we got it. Now we have to talk about add eax. Okay. So let us see here where is 0 1. As sorry, our code leads to 0 1. So where is 0 1? So if you see 0 1 is here. So it will have similar kind of representation which we had for move. So here move was replaced to add. Now it was earlier as move R32 to RM32. Same case is here, add R32 to RM32. So this is the code that we got. So in the same way, if we see this would be the 0 1 and this slash r tells you that there would be mod rm involved. So if even we see move instruction, so let us see move. So we got 89. So 89 would be here. So this is 89 opcode which is picked in that case. So the way that I said move R32 RM32. So slash r is there, that means it tells you that this is register involved over there. So what we will do, we will not use this for a while and we will write some code. Again I will manipulate, I will take one sample code again, Emacs test 1.asm. Now I will change the register. So let us say section dot text global main, then let me change the register, move ECX comma EDX, move ESI comma EDI, move ESP comma EBP and so on. Now let us try and translate this code. Fine. So we have these numbers. Fine. So I will remove this. I will remove this as well. Now we have these registers available with us. Now if I have to write move ECX comma EDX. So as we have said that we will have to write it in a cross. So what is EDX representation? We will write it here. What is ECX representation? We write here. Fine. And what was our mod? So it was 110100. So if it is this one, so let us divide this into group of 4 bits. Now let us write its hex representation. So ECX comma EDX. So 1101. So 8 plus 4 12, 12 plus 1 3, D 13, 12 plus 1 13. So now EDX would be what? 1. So when we see move ECX comma EDX, opcode along with it D1 should occur. Now next instruction we have taken is ESI comma EDI. Again take it in cross. So EDI would be 111. ESI is what? ESI would be 110. So let us add mod as 11. Let us take this. So we got what? So this would be what? F, correct. So this would be F and 8 plus 4 12 plus 2 14. 14 is E. So we should somehow get FE. Let us try to see whether we will get it or not. Next one is ESP EBP. Again in cross. ESP EBP's number is 101. ESP is 100. So let us write this. Let us divide. Let us get this. So 8 plus 4 12 plus 2 14. So it is E. Then 8 plus 4 12 means ABC. So let us try and see whether are we getting similar thing. So let me translate this to again an LST file. So I will say P1. So less P1 dot LST. Now see the code. ECX EDX it had D1. For ESI EDI it had FE, and for ESP EBP it had EC. So if you see over here, same things are carried out. So when we had ECX EDX, we got object code as we got ModRM byte as D1. ESI EDI we got FE, and then ESP EBP we got EC. So similarly, you can compute this ModRM for all instructions where ModRM would be necessary. So mainly like I have picked here move. So same way you may use in place of move, you may use add, sub and so on, which do all instructions where two registers can be used as an operand can be picked over here, but we have to specifically see that that instruction will require mod RM byte. Now, how we will know this? So, if we see the way that instructions are defined in Intel manual, every instruction when it was described is in a tabular form here. So, you will see that along with the opcode, if /r is written, every time mod RM would be included there. So, these instructions would definitely require mod RM byte. Now, we will take one another example where now this case we have taken as say both the parameters to be registers. Now, I am going to take another example where I will change my operand types now. So, let us take Emacs test 2, let us write this section dot text. Now, let me write global main, then move. I am writing this, I am pushing, I am moving value 10 to say a register EAX. So, same way I will write one other instruction, move EBX comma 11, okay, let us take 10 only. So, move ECX comma 10, move EDX comma 10. So, even you can see ESI comma 10, move EDI comma 10. Okay, now these instructions look to be similar. Now, in this case we are having immediate data included into this instruction. Now, how exactly this translation would be done? So, let us save this and now translate using translator. So, I am taking this p2.lst. So, less p2.lst. Now, see here like move EAX comma 10, as we have taken 10 as a same digit in across all the instructions. One may see here that there is 0A 0, the way that we earlier even saw 0A 0 0 0 is included, same cases here, every instruction is containing this. Now, it would be surprise for you to see that earlier we had before the with the instruction we had 4 bytes, correct. Now, if 10 is represented here as 0A 0 0 0 0 0 0, then definitely what is appearing before it is an opcode. Okay. Now, this instruction when there is an immediate data involved, this does not require at all the mod RM byte. This is specific. Let us understand this. Whenever we have immediate data included in the instruction, at the translation time we are not going to take care of mod RM byte at all. So, mod RM byte would be removed. Now, what is remaining is opcode only. Now, we even one can check here, like when we see move EX comma 10. So, opcode generated for it is B8, then BB, then B9, then BA, then BE, then BF. Now, if I write these codes with my register order above, like when we said these are the registers that I have included. So, let me write this B8, okay, which I got when I had a register comma immediate, okay, which itself is a 32-bit value, fine. Then I got let me take ECX now. ECX in this case is move ECX comma 10. So, what it is B9 again. So, I will write this, copy, paste. So, we saw that this is B9 and here the register is CX. So, now you can directly tell for DX it would be BA. So, EDX comma immediate 32, then BA, then EDX after EDX you get BB, which is EBX comma immediate 32, fine. Then BC, which is the next number after EBX, ESP. So, as we haven't included ESP, so ESP and EBP would go here. Now, ESI is 110, after B it would be BE, okay. This is again ESI comma immediate 32, then BF ESI comma immediate 32, sorry, this is EDI. Now there is some consistency over here. If you see this, the representation that I wrote here, B8, B9, BA, BB, BCBD, as we haven't included ESP and EBP in our instructions, so I am not considering them for a while. So there is a BE and BF. Now if you see, initially it was B8, then it seems there is some number added there. So B8 plus 1 I got B9, B8 plus 2 I got BA. Now if you see what are the register numbers are, let me give them numbers 0, 1, 2, then I have 3, then 4, then 5, then 6 and then this is 7. So if I add that 7 into B8, so EDI should be 8 plus 7, 15, so BF ultimately, correct. So that means what? Opcode for all instruction where the format is move register 32 comma immediate 32, opcode would be B8 plus now the register number. Now if I add, what is the register number for EX? It is 000. So if I add 0 into B8, so ultimately it will result to B8 only. If whenever my register number is 1 for ECX, so whenever ECX and immediate data is there for 32 bit, then it will be B9 and so on. So let us see whether is it the same case what one can see over. We have to justify, we have to find out whether is whatever I have written is correct or not. So this is the opcode generated here. Now let us see that opcode. So let us find out B8. So we got it here. So let us see this. What we are saying is, read the description given for the instruction. It says move immediate 32 bit data to register 32 bit. So that is what we did rather, correct. So we tried moving 32 bit value into a 32 bit register. Now if we see over here why there is no ModRM byte. So here with B8 you may see here it is saying plus RD. Now slash R is not written. Now this itself is telling us that ModRM byte is not included in the instruction. So this RD, this is plus RD, that means what? This B8 would be same across the register, only you have to add register number there. What are the register number that we saw in earlier case? Like in this case we said 0, 1, 2, 3, 4, 5, 6, 7 in the same order, the way that we are referring these registers as. Fine. So if now let us change the instruction, like earlier we had move, let me change it to say, we will change it to test3 dot ASM. So Emacs test3 dot ASM LG replace string, we want to replace each move, replace string, replace move by add. So we got this. So let us try to translate this. Now is it same? So we should see some change over there. So this would be P test3 p3.lst less p3.lst. Now let us see the code. Now suddenly the way that we saw in move instruction, 10 was written in using some pattern. Now in this case if you see, code is now bigger. Now we can see here as 10 is included in each of the instruction, this 0A, one may say that this 0A represents that 10 now. Now why it took only 1 byte? Because in add instruction, this is major difference between move and add when they get translated. With move, when your register is 32 bit and if data is whatever the number of byte it takes, it will always take 4 bytes to represent that number. Whether that number gets fitted into 1 byte or 2 byte, it does not care that time, it will be always fitting into 4 bytes. This case is somewhat different into add instruction. So add instruction will take only those number of bytes to represent immediate data, what are the number of bytes required to store that immediate value. So in this case as 10 is the common value that we took, so this 10 would be stored over there, fine, as an a 0A. Now this major difference, earlier we saw with move 0A 0 0 0 0 0 0, now it would be what? 0A only, it would not be taking all those remaining bytes, fine. So this is correct. Now second thing is like we have 0A. Now one may see here that there is something common 83. For add, all add we got 83. Now what is changing is C0, C3, C1, C2, C6, C7. Now what exactly this is? So let us try to write, we will apply reverse engineering in this case. So I will remove this. Now what the code says? Code says C0, then next was C3, C1, C2. So we will move this EBX, we know that it is EBX, so we will move it here. Then after C3 it is C4 and 5 is not there because we have not taken SP and EBP, ESP and EBP. So C7. Now if I try writing this C0, so how will I represent this? C means what? Like A, B, C. So it is 8 plus 4 plus 1. So A is 10, B is 11, C B is 11, C is 12. So 8 plus 4 and then remaining bit 0, and all the remaining bits also would be 0. So your code would be what? Would be divided in this case. Like fine, let us talk about C1, 1 1 0 0, and for 1 we will be having 0 0 0 1. Now let us take C2, 1 1 0 0. Now code is what? 0 0 1 0. For C3, 1 1 0 0, 0 0 1 1. For C6, 1 1 0 0, 6 would be what? 0 1 2 6, means 4 plus 2 6, 1 1 0 0. So 0 1 1 1. Now you may see here like these, if I divide this as a group of 3 bits, then let me combine this together. Now our instruction was what? Move register comma immediate. Okay. So again in cross thing, like a register would be written, register number would be written here. For immediate, as it is a immediate value, so this 0 0 0 is constant across all the instructions, fine. And then in this case, whenever you have something different, like we always even said immediate or whatever, like in this case we got again mod as 1 1. So when we had register to register, when we had register to immediate or immediate to register, same case like for both these categories, mod would be 1 1, fine. So this is what is one important thing. So this case I can tell that in this case EX is a particular register used, this is ECX used. So this is EDX, this is EBX, this is ESI. You may see here like 110 represents ESI, so ESI, and 111 represents EDI. So ultimately our instructions are now like this: move EX comma something. We do not know what that data is. So if I see this kind of code, I should be able to reverse engineer it. So that is what I am doing now, move ECX comma. So this instruction should look like as move EDX comma, fine. Same case, move EBX comma, then move ESI comma, and then move EDI comma. So no matter what is immediate value, that value would be added here, and that value for this case would be added here. Now if you see in the instruction format, what we saw on in the initial stage, like in the chapter number 2, this instruction format contains opcode, which we already saw a case, ModRM, even we saw this, and there is something towards the end is immediate. Now this would be the particular place where your immediate data would be represented into hex, fine. So this either would be 1 byte, 2 byte or 4 byte, fine. So even if we see here, most of the instructions which we are going to see in first few sessions would be most of the times always 1 byte. We will be taking some examples towards say after 5-6 sessions where there would be requirement of having more than 1 byte to represent an opcode itself. So one may see here, like when opcode is written, there is description given. Opcode can be a 1 byte opcode, 2 byte opcode or 3 byte opcode. Mod RM would be always 1 byte. SIB, which we are going to again see in our next session, where there will be scale, index and base required. SIB is scale, index, base. Again it is divided in similar fashion like mod RM byte, about which in detail we will be talking later. Displacement would be some address displacement included. In terms of number of bytes even, again 1 byte, 2 byte or 4 byte. Okay. And immediate data would be 1, 2 or 4, and you importantly can see over here there is none written, correct. So, some instructions would be having no address or displacement mentioned, but automatically internally they would be taking it. So, we will be seeing few of such instructions where address actually is included, but that address would not be shown as an bytes represented for that particular address. Fine. So, this ends our first session. In next session rather, we will talk about further more instructions where there would be some representation using this mod RM byte. We will put more focus on this mod RM byte, and we will see how this mod RM byte can be used in the reverse manner. So, next session dedicatedly would be what? We will be picking opcode, and from that opcode we will try to write what exactly the code is. Thank you.